Hello, so today we're going to look at a quantum mechanics question where we have to find the expectation value of x of this function. So the first thing we're going to need to do to find this is to normalize for our value of a. So we know that the sum over the entire space should equal 1. So 1 is equal to minus infinity to infinity a e to the minus lambda x minus a squared. Now notice that we didn't square the function here, and that's because this is the actual distribution we want to compute. It's not an eigenstate that we want to compute. So we can do this by letting u equal x minus a, du equals dx. Then we find that 1 is equal to a times the integral minus infinity to infinity e to the minus lambda u squared du. Now this is an elementary integral. We know this from a typical Gaussian table. If you want to do this in polar coordinates, it's also possible. But generally your teachers are not going to expect you to do this by hand. So we know this is equal to a times the square root of pi over lambda. Therefore, we can solve for a to be the square root of lambda over pi. So now that we have a, we can continue finding the expectation value of x. So the expectation value is given to be the integral over all space of our function, which is rho in this case, and x dx. So just computing this would be the integral from minus infinity to infinity of x e to the minus lambda x minus a squared dx. Now, as before, we just take u to be equal to x minus a. Then we know that u plus a is equal to x, and as before, du is equal to dx. So our expectation value is equal to the integral from minus infinity to infinity of u plus a e to the minus lambda u squared du. Notice we can split this up into two separate integrals. Now, we know that this integral is an even function because of this. Hence, all the values on the left-hand side of 0 will cancel out with all the values on the right-hand side of 0. So we know that this function just goes to 0. So we're only interested in this value. And as before, we know what this integral is because we've done it before here. So we can see that this integral is just simply equal to the square root of a lambda over pi times a. Now we can substitute our value of a here. And notice that these two will cancel out and we just get a, which is our expectation value of x.